Good afternoon, this is Schweitzer, and we're looking to run through some answers on thermodynamic equations and calculations. So we're looking to utilize our specific heat and our formulas to solve some stoichiometry and some things here. 5 grams H2 is burned in excess oxygen, causing 2,000 grams of water to increase increase that much temperature. Write a balanced equation. All right, so in this case, it's H2 plus O2 yields H2O. All right. Next, we balance it, so we're going to need a 2 here and a 2 here. How much energy did the water gain? So in this case, we can do our known, unknown table. So it's a good application of some of the stuff that we just learned. And it looks like the water would be our known, so it's going to use the formula Q equals mass times change in temperature times heat. I'm not really going to use this table. You could run through something like that if you want, but I'm just going to use this. Mass of the water is 2,000 grams, and the change temperature is 85. The speed heat of water is 4.18, and therefore my answer is, grab your calculator, looks like we got 710,000. So 710,600 joules of energy. You could also say 710 kilojoules. How many moles of H2 are being consumed? Okay, so in this case, we have to look at the stoichiometry here. It says we have 5 grams of hydrogen. So all we gotta do is say 5 grams, dot line, get rid of grams, go to moles. 1 mole is 2 grams, and therefore 2.5 moles. How much energy is being absorbed per mole? So we want to take these two guys and divide them. So it's going to be 710,600. We'll do it in joules. Joules per mole, and this is 2.5 moles. So 2.5 moles of hydrogen is consumed, and we're getting out that much energy. So divide those two out to get our ratio of joules per 1 mole divided by 2.5 is 284,000 is 284,000 and 240. That would be joules per mole, or it would be 284 kilojoules per mole. So, okay. What is the enthalpy in kilojoules? Okay. Now for this particular reaction, this is the amount of energy when 1 mole of hydrogen is burned. Okay, right there. So we could do a ratio here like this. If 1 mole of hydrogen gives us 284 kilojoules of energy, what would 2 moles get us through? 2 moles is just going to be double that. So 2 times 284 would be solving for that piece there. We just double that. So times 2 is 568 kilojoules. So 568 kilojoules. And that's per reaction cycle. That is really only for this particular reaction right there. Okay. Now that's the enthalpy. So kilojoules per mole is one thing. That's not the enthalpy unless you're only burning 1 mole of something, and that's the same thing. But Next one, 25 grams of hydrogen is burned. How much energy is produced? Okay, we can do that. 25 grams. Okay, get rid of grams and go to moles. Now we know that 5 grams gave us this much energy. So 25 would technically be 5 times that. Let's do the math here. 1 mole is 2 grams equals 5 times as much stuff. So 25 divided by 2 is 12.5. So 12.5 goes here. 12.5 moles. And you would note that's 5 times more moles than that. It should be, yep. And then for every, now we use the delta H here. So, or a ratio, I could use 1 to 284 or 2 to 568. I'll use the delta H we just got. 2 moles gives me 568 kilojoules. Now again, I could have used 1 to 284, it's the same ratio. And then that guy times 568 divided by 2 equals 3550. So 3,550 kilojoules of energy. And that is that answer. All right. How much energy is produced when 2 moles of methanol is burned? So now we're just giving me the delta H. So that last problem, we did an experiment where we collected the energy for this. Now they're just giving it to us. Now that's one cycle through this process. How much energy is produced when 2 moles of methanol is burned? That's that stuff right there. Well, 2 moles gives us that much energy. So it's just negative 1452. How much energy would it be when 1 mole is burned? Okay, well, again, you could do it the long way and say 1 mole. Okay, get rid of moles and go to kilojoules of energy. This is the delta H here. That's a 2 moles gives us 1452. The negative is just the direction, it's exothermic. And you run it through and you're going to get half that. Now that's one way of doing it. Or you could say, well, how much is 1 mole? Well, 2 moles gives us 1452. How much would 1 mole give us? And you would just cross multiply and divide. Or it's just straight proportions, half as much. So 1452 divided by 2 is 726. And it would be 726. Of course, it would just be negative, meaning that it's exothermic. How much energy is produced when 16 grams of methanol is burned? Okay. So you could do some math here and figure out how many grams gave you that much, and you could do a proportion off that. We typically just do it this way. 16 grams, dotted line, get rid of grams, and go to moles. The reason why we go to moles is because I want to use the 2 moles to 1450 ratio. So 1 mole, how much does this stuff weigh? So it's, the carbon is going to give us 12 plus 3 for the hydrogen plus 16 plus 1 more for the hydrogen is 32. Okay, so 16 divided by 32 looks like that's about half a mole. So 0.5 moles. Now this is how many moles we're going to process through this thing. So 2 moles gave us that much. How much would 0.5 moles give us? All right, get rid of moles and go to kilojoules. 2 moles gives us 1452. And there we go. So 16 divided by 32, of course, is 0.5. Divided by 2 times 1452 gives us 363 kilojoules of energy. 363 kilojoules of energy. Okay. That a little nicer, 363. That's kilojoules. All right. Next. Eventually get there. All right. How much would 100 grams of water increase in temperature if 20 grams of methanol is burned in heating water? Okay. So we just do this. Q equals mass times change in temperature times specific heat. And I have everything except I need this change in temperature. So this is going to be, and has to be in joules. So 363,000 equals the mass of, hold on a second, 20 grams. So let's back this up a second here. I can't use that 363 because I'm going to have this at 20 grams, so versus 16 here. In fact, let's just change this to 16. All right, yours will be changed. We'll change it 16 grams. All right, that way we can just same energy. So same problem. 363,000, no sense changing it, joules equals the mass of 100 grams of water we're warming up. We're looking for delta T, and the specific heat of water is 4.18. And now we just solve for delta T. And my delta T is, so 363,000 divided by 100 divided by 4.18, and it's 868 degrees. So this is delta T equals 868 degrees Celsius. Now that's not really all that feasible because this thing would boil first. It would definitely boil before that happened. Next up, we have 50 grams of methane. Okay, try it out. So let's write out a reaction, determine the enthalpy of combustion of methane. So write out a reaction, determine that. So it says here, when 50 grams of methane is burned, we get this much energy released. Okay, so let's do this. CH4 plus O2 yields CO2 plus H2O. We got 2 hydrogens, so we need a 2 here. 2 and 2 is 4, so I need a 2 here. And saying here that 50, so it's balanced here, so 50 grams, let's convert that to moles. So let's do that right here, 50 grams, get rid of grams and go to moles. 1 mole equals 16 grams per mole. That's the molar mass of methane. So we're going to do 50 divided by 16 equals 3.12 moles. 3.12 moles gave us this much energy. So the Q per mole equals 2.78 divided by 3.12, and let's do that. It's in kilojoules, by the way. 2.78 divided by 3.12 equals 0.89 equals, all right, 0.89 kilojoules per mole. So in that case, it would be 890 joules per mole. And since we're only using 1 mole of this item to process through, this also is the delta H for that reaction. And it's a burning reaction, so it's going to be negative. And there we go. Ethanol, how how much energy would be released with 36 grams? Now, you can go via moles if you want. We know 50 equals that. So let's just do a straight proportion. 50 grams gives me 2.78. What would 36 give me? All right. Cross, multiply, and divide. 36 times 2.78 divided by 50 is 2. All right. So my answer here is 2. And that would be kilojoules of energy. And that's the answer for B. All right. Ethanol requires energy to be vaporized from liquid to a gas. That's solid, liquid, and gas. So we're going to jump from here to here. Okay. And there's this called a delta H of vaporization. And in this situation, whenever you see something written below that, sometimes it causes people to get a little bit nervous, like, oh no, what do I do? It's no big deal. Just okay, well, it just tells me a little bit about the type of reaction that we're dealing with here. Okay, so it says it's being vaporized. 100 gram sample of ethanol has 100 grams evaporated away. How much cooler will must the original ethanol be? Okay. So in this situation here, okay, we have 38.5 kilojoules. It's almost always in kilojoules per reaction cycle. So 1 mole of liquid goes to 1 mole of gas. 38 kilojoules of energy is what is required to make that conversion. Okay, so let's do it this way. Let's figure out the energy. Same as always, 100 grams. I want to use that 1 mole to that energy. Get rid of grams and go to moles. 1 mole is 38.5 grams. I know that I get 38 grams for every 1 mole, and looks like I'm grabbing the wrong number here. I did. Let's add up the molar mass here for ethanol. I didn't do that. I grabbed the wrong number. So 1 mole, but I caught that. So let's add this up here. We got 12 plus 12 is 24. This guy is 6. This guy is 16. And this guy is 1. So, or 5. So 24 plus, and those two combined is 6. 6 plus 16 is 46. Okay. So we got 46 grams. And then for every 1 mole that I'm converting, I am going to be requiring 38.5 kilojoules of energy. Okay. I only, of the 100 grams, I only evaporated away 100 grams of it. That's why I have the 100 there. So 100 divided by 46 times 38.5 gives me 83.6 kilojoules of energy. So 83.6 kilojoules of energy. All right, so at this point, you have to know we want to cool this thing down. So in order to cool it down, we're going to need to know the specific heat of this substance, ethanol. I don't know if I have a table of this or not. If I don't, then I will add it into your sheet. And I do. Okay. So we have 900 grams of this. Okay, so now we're going to use this equation. Q equals mass times change in temperature times specific heat. And the mass is 900. This thing lost 83.6 83.6. So, and then looking for the change in temperature, and then specific heat C. Okay, for looking for ethanol. Ethanol is 2.4. Okay, so that I had to look on a table for that, and I'll add it in here for you. All right, and equals. Okay, solve all for delta T. Now the 83.6 is in kilojoules, and the specific heat is in joules. So this is going to have to be converted 83,600,123, and this is now joules. So I'm going to divide the 900 out, divide the 2.4, and we'll know how much it changes in temperature. So 83.6 divided by or times 1,000 got me to my 83,600. Divided by 900 divided by 2.4, and I get 38.7 degrees. So it's changed in temperature 38.7 degrees Celsius. All right, and that's my answer. Thank you very much.